Welcome everyone to Science Thursdays with Brookhaven Lab. The purpose of Science Thursdays is to engage our student and education community in STEM topics by meeting via Brookhaven Lab STEM professionals and learn more about their work, career path that got them to where they are today. At the end of the 45 minutes, we hope that you have heard something that will spark your interest in a STEM career and perhaps consider being part of the Brookhaven Lab community. Good afternoon. My name is Aleida Perez from the Office of Educational Program. And before I introduce our today's guest, a few reminders. You're welcome to submit your questions on the Q&A chat section. It's at the bottom bar of the Zoom app. We will try to get as many questions as we can possibly get today. And if you have any issues with difficulties with the video stream, you can let IT know. We are grateful to have George Canales and Sal Gonzalez supporting us today. Let them know by making a comment on the chat section, on this chat area. So today I am joined by Justine Haupt. She's an instrument engineer and the instrumentation division at Brookhaven Lab. It's a pleasure to have her today. Justine will share her work in the various projects related to instrument development used in cosmology and survey of the universe, and in her current project related to the quantum initiative. And we will also discuss with her career path. Welcome, Justine. How are you?
I am good.
It is a true pleasure having you here today. I know that we have done a lot of stuff together in our office for our students outreach. I'm very grateful and thankful that you are joining us today. I think this will be a very good and cool conversation to have with our students. So today I'm looking forward to it. Justine, I mentioned that you work at the instrumentation division here at Brookhaven Lab, and people might not be aware that, or may not even know that the instrumentation division has been part of Brookhaven Lab for as long as the lab have existed, about 70 years or so. Can you tell us a little bit about what is the instrumentation division and the kind of work that it does to support science?
Yeah, absolutely. Basically, well, we're instrument developers, so we excuse me. So we we build the scientific experiments. You think. Okay, let me be more clear. So you have you're doing science. You have experiments. Experiments require experimental hardware. So we specialize in building experimental hardware and building scientific equipment. Telescopes, detectors, anything cutting edge that hasn't existed before, some things you can't just buy, things that need to be created, and things which of their own right become usually research endeavors, pushing the limits of what can be done from an experimental science perspective.
Actually, I love the way you describe it, because that's, all those instruments, those detectors, all those tools that you said as used not just by Brookhaven Lab scientists, but by other scientists as well around, around the world. So that's actually a very important role, important job here.
Yes, and
go ahead.
I can't forget to mention that we also in instrumentation division invented the video games.
Yes.
The video game.
Yeah. Yes, that is true. The tennis for two, right? So that was part
Yes.
of the instrumentation division as well. What is your role at the instrumentation? And what do you do there? What is your role in the department?
Well, I'm a science associate. I'm kind of I develop kind of, it's the crossroads between engineering and experimental science, where you're for me in particular, I'm doing everything from optical system research and design and electronics and mechanical things, and kind of just a little bit of a an all-purpose engineer combined with doing some research. So and in particular, I've worked on optical and radio astronomy telescopes, and now on quantum communications hardware, which actually has some overlap with optical astronomy instrumentation, and drones, actually anything fun, basically.
I know I have known you since I've probably been here at BNL. That will be 2013 or so. So I know that the stuff that you do it's pretty fun, and it's very cutting edge, and also has very important applications or implications for the science that we do. So one of the things that I learned about you when I first met you back in those days, you were working, or you were involved in the very cool project at that time, which is the Vera Rubin Observatory, the LSST project at that time. So can you talk to us a little bit about what is, because we play a very important role in that project, in that collaboration. Can you tell us a bit about the role that we and you, BNL, Brookhaven Lab, and you play on that particular project, and what is its mission? And before you answer that, it's a question about what is the beeping going on behind Justine. It's her computer fan, right?
Well, yeah, is it beeping? I didn't.
It's a beeping.
Oh, then I don't know if it is me then, because yeah, my fan is making a tone, but it's not beeping. I don't know.
It might be your computer. So I think I think so. So it will be good. So
okay, ignore the beeping. I can't hear it. Sorry.
So what about the Vera Rubin LSST? What was your role? What is it? What was the big piece of hardware that were part of it?
Well, we developed, so this is a large 8-meter class telescope, which actually isn't the biggest anymore, but the camera on the telescope is, we've always said, is the biggest camera ever built, and that's a key part of the camera is what we've developed at Brookhaven. So the camera for this telescope is like, it's bigger than a car. The lenses, there's 3 lenses, the biggest of which is over 1.5 meters in diameter, which is actually the largest lens ever fabricated from what we can tell. And we at Brookhaven developed the sensors. So if you have your smartphone with a camera in it, or a digital camera, the sensor chip, the thing that actually is sensitive to light and records the image, is what we built. The sensors, the electronics, it's a cryogenic instrument, so it's operated in vacuum at very low temperatures, and it's quite big. It's 63 centimeters across, so it's actually a mosaic of many smaller sensors. And so if you can picture the sensor in your phone, which is probably a few millimeters square, ours is like that. It's gigapixels.
Yeah. And so what is this mission of it? So what is the goal of the project itself? The LSST, the Vera Rubin, yeah.
It was originally envisioned as a dark energy survey telescope, and that sounds suspicious because you can't see dark energy, but there are ways of doing dark energy research by looking at the sky. But it turned into, over time, over the course of the development process, a multi-objective instrument. So mainly dark energy and dark matter research, both of which you can do research on by indirect observation. You can actually see dark matter, and certainly not dark energy, but you can come to conclusions about their nature. And additionally, transient research, which is one of the interesting things this telescope does, is that it will be recording more or less a cosmic time lapse, of the entire night sky over its initial 10-year observing run, where you have a snapshot every 3 nights of the entire sky. So you expect to see things move on cosmic scales that you wouldn't have expected to move, and so we expect to see a lot of things. It'll discover plenty of near-Earth asteroids and other asteroids and comets and potentially hazardous objects, but also things you might not have expected to see moving. So maybe some interesting new science there. You don't really know. But dark matter, dark energy, transient research, that kind of thing.
Yeah, and and one thing for our audience is that it also takes a survey of the sky. Some of this data will be available to the public once the experiment starts to collect information. So so that's something that will be available for the public as well, to be participant of that.
Yeah, totally open source.
Mm-hmm. Open source.
Right, a public facing web page to have telescope data accessible, raw data be accessible by everyone pretty soon after images are actually taken. It's not proprietary information. And actually with science like this, that there's so much data coming in, it's professional astronomers alone have a hard time keeping track of it and discovering new things. You wind up having to spend all your time automating the process of characterizing the images and of discovery. So having as many fresh eyes on it as possible, actually, I think there's a history of this in astronomy where amateurs have typically made contributions by finding new things and continue to do so, whether it's in their own backyard or looking at data from larger projects like this one.
That's very cool. And so the project, the LSST, the Vera Rubin will come online sometime in the next year or so, I believe so. So I think that will be something for all of us to look into. So I do want to give some time to the questions. So let me just ask you another question before we move. Another cool project that you've been working on is the Baryon mapping experiment. It's called the BMX. And that's a project that it started from the grounds up at the lab at Brookhaven Lab, where you were part of the group that's built this very cool radio telescope, right?
Yeah.
In on sites. Can you tell us a little bit about the prototype, about what the project is and where the project is heading?
Yeah. Should I share any pictures at this point?
Yes, you can do.
Okay. Well, let me show a picture of what the Baryon mapping experiment is. This is a radio telescope. Some of us who worked on the Vera Rubin Observatory, LSST, were thinking about what the next thing would be, and seems like one of the next things to really think about is doing this cosmic research in the radio domain using a radio telescope. So let me share. Let's see, share screen. Share screen. Oh, no, of course it's not sharing what I thought. Yeah, so you see this picture?
Yes.
Okay, so that is the Baryon mapping experiment. This is a very small radio telescope. It's fixed. It doesn't look like what you usually think of when you think of a radio telescope, which, if you picture what you see in the movie Contact, the Jodie Foster movie, one of my favorites, it's quite different. It's just pointing up. And so we rely on the rotation of the Earth to scan across the sky. And this has been basically a demonstrator instrument to develop the sensitive enough instrumentation to be able to detect the signal we're trying to find, which is extremely weak. The point of this is to, do I have more pictures? The point of this, maybe not of this actually, the point of this telescope is to develop the instrumentation to be able to detect an emission line from hydrogen. So hydrogen has emission lines in the visible light, but also in radio at 21 centimeters wavelength. Let me see what it looks like. I'll unshare that. And at 21 centimeters wavelength. So, and hydrogen is emitting this throughout the universe all the way, and hydrogen was the first abundant, the first element to form in the universe. So there's a potential to trace the density of hydrogen all the way back to almost the beginning of time, the beginning of the universe. But it's a very, very weak signal, and our own galaxy is a bright foreground, light pollution source really for this hydrogen emission. So the task will be developing an instrument that's sensitive enough to be able to see through our own galactic, our own sky. So it's exciting, and actually it also. Oh, that was the other reshare. Sure. Yeah, this also led to some drone activity. Oops. Hey Hey, buddy. There's a cat next to me. Oh, he's walking on the keyboard. Oh, okay, he's gone. Trying to find the drone. Where's the drone? Here's the drone. Okay, so this is when it was in an earlier state, but the idea here is to use this to calibrate the radio telescope, because we don't know how sensitive the telescope is with respect to where it's looking at the sky. So the idea is that you take a known radio source, you suspend it from the drone, and you fly the drone in a known pattern over the telescope, and then you can use that to calibrate your telescope.
See how sensitive it is, that signal that you're getting or expect to get from. This is very cool.
Yeah.
That is actually very cool. And so I know that, you know, one of the goals is just to have multiples of these radio telescopes. Like I think about it, like you mentioned, contact, and many of them to create the to have the sensitivity to make those to detect those signals further. I know that that's something that is in the works and not quite there yet, but I think it will be exciting for all of us to know, to learn more about it when the time comes about the array that you know, that is the follow-up to this.
Yeah,
project.
actually, it looks like the follow-up might wind up being an experiment on the dark side of the moon, and we're working with Berkeley on that. But I don't think I'm supposed to say anything about that yet.
Then we won't say anymore.
Okay.
Very cool. Other things that I you know, that I think when I talk to you before when I get to some of the cool questions that we have about the work that you're doing, is that you are a recipient of some funds that the laboratory, the directed research and development program at Brookhaven Lab. So those are funds that are given to scientists and to competitive way to acknowledge innovative and exploratory research. So congratulations on that. And I know that when you and I talked about it, that project is related to the quantum initiative at the laboratory. So can you tell us a little bit, what is it that you're going to be doing next?
Yeah, this is really exciting. Quantum communications, you know. So what is that? It means you know, using. Okay, so what does it mean? So most people, I think, at this point have heard of quantum computers, even if you don't know what it is or what it's for. Maybe you've heard of this. And the basic premise is that if you have a world where quantum computers exist, you want to network them to take full advantage of the technology. And if you network quantum computers, it has to be done in a way that preserves the quantum properties. So you wind up in a situation where you need to do quantum networking, meaning entangling quantum states over long regional distances between universities, between labs, whatever. It turns out that the easiest, at least for now, the easiest way of transmitting quantum states between computers is with light, with photons. So we use fiber optics and also telescopes, which is where I come in, or we're trying to anyway, to actually entangle photons over long distances. So to start with, this project that I'm a part of, and which I have the LDRD funding for, subpart of, is to create a quantum network between Stony Brook University and Brookhaven Lab. It's about 20 kilometers. It's a big project, a lot of people working on it. My part of it is specifically trying to build a telescope system, which we can put on the roof of the hospital tower at Stony Brook University, which is the tallest building there, and the tallest building at Brookhaven Lab. They can see each other. Oh, pictures. I have to show a picture. They can see each other. We can see each other institution. So from the roof of the tallest building at Brookhaven Lab, looking through a long telephoto camera lens, you can see the hospital towers at Stony Brook University, which is what we see now. And you just cleared the tree line, luckily. So the idea is we put a telescope on one of these roofs. Actually, it's going to be the middle one here. And another telescope on the roof at Brookhaven Lab, which I think I did not supply a picture of, and try to be able to record individual photons traveling across that distance and entangle them with photons in the respective labs at Stony Brook and Brookhaven to be able to do quantum communication. Right now, we're doing a lot of lab work. This is a smaller scale version of this, which I've been working on with some students and such, and doing some tests over the length of the actually in the main hallway in the instrumentation division. And then the next step will be to build a much larger version of the system for the rooftop. And
when do you hope to have that installed on the rooftops of either building?
Well, we were hoping to have the building, like the lab, the shack that we were going to work in, erected last year, and you know, it's kind of taking a while, but it should go. That will be built this year, and then for early next year, we'll actually install the instruments, the large telescopes, and all the exotic equipment that we need to try to make this work. So this is a 3-year project. It was funded for 3 years. We just started the second year. So in 2023, hopefully the rooftop system will be coming together, and by the end of the year, hopefully demonstrated to be operational. So it's very exciting to me. I mean, it's
cool.
Yeah,
very exciting.
And actually, this has application to astronomy too, because if you can do quantum communication, you can do some amazing things with making very high resolution images. It's not just about quantum computers talking to each other. It's about pushing past the classical limit of taking measurements, basically, in general.
Correct.
Yeah,
that's in high imaging in astronomy is very important too. The detail is needed.
Yeah, we want to take more pictures of black holes, right? Yeah.
So and then so I am going to ask you a question. I know you're an inventor and an astronomer. I know you're a member. You are part of the Custer Institute here in Long Island, and you have done some very cool things. So can you I know that you invented a phone, and you can talk a little bit about that. I also know that, like I said, you're an astronomer, and you are part of the Custer Institute. There's a question in the chat that I think is appropriate to ask now: has there ever been a radio signal from space detected that is awe-inspiring in some way?
Has there ever been? A lot of times, I would say. I mean, to me, okay. Yeah, well, okay, awe-inspiring. I mean, to me, just pulsars are awe-inspiring when you think about what's going on with pulsars. I mean, they're all awe-inspiring. Come on.
It's like picking your favorite child, right?
Yeah. I mean, pulsars is an obvious one. Obviously, everyone wants to see a SETI signal, and that hasn't happened. But who knows? That's at least not considered a quackery anymore. It's kind of bona fide science. Yeah, I mean, I don't know that I have one. I'm not. My background isn't in radio astronomy. It's something I got into as an instrument developer, and because I you know, it's very you know, the whole topic is awe-inspiring.
It's very, 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 very cool. So I just want to touch base about the fact that you're an inventor. You come up with this this amazing creative things that you come together. So you talk about the telephone. Can you tell us a little bit about the telephone that you invented?
Yeah, the telephone. I don't like to say invented because it's such a silly. It was a silly side project that I made for myself. Shoot, I don't have it. I have like pieces of prototypes all over the place, and I don't have a full one to show you right now. So a few years ago, I made myself a rotary cell phone, just so I'd have my own rotary cell phone because I don't like smartphones. Let me share some pictures. And then I posted some pictures on my own personal website, and people like went crazy for it. And I was trying to start a company anyway, like an open source company. So I decided it kind of turned into a product. So this is the rotary cell phone. This is actually, all right, this picture is hard to see. This is actually quite small. It's small enough to fit in your pocket. And it looks like a production thing, right? It doesn't look like something somebody made. Yeah, it's because it took a lot of work to design it. You know, doing the electrical design, the circuit board layout, having all of these gears, all these mechanical pieces. Those are all I designed them and had them injection molded in quantities of thousands at a time. These flywheel weights here. The springs are custom. The enclosure is custom. It's all injection molded parts. Actually, so I have some parts I can show. What do we have here? What do we have here? Right. Oh, Okay, like here is this is just gives you a sense of how big it is. This
Yes.
is the
Oh, very cool.
and the hard parts of the injection molded pieces, but you know, it fits in your hand. Here's some more prototype pieces. So this was like originally a 3D printed thing, and the design was a bit different, and people went crazy for it, and I thought it was kind of dumb. I mean, I thought it was cool because I made it for myself, but I would never have considered mass producing it. And I can't tell you how many emails I got from people just wanting to give me bags of money if only I could make them one.
There's a question in the chat, Justine, that asks, can it fit SIM cards?
Yeah, it takes a standard kind of the typical size SIM card, which
very cool.
Yeah, I mean that's how you get a sign on with a cell phone carrier with a bring your own device service, and then they send you a SIM card that has a phone number attached to it. The daughter board isn't here. I can't really show. Oh, here it is. That has a SIM that has a phone number attached to it, and then that's how you get it to work on a pre-existing carrier. Hold on, this isn't meant to be. I wasn't prepared for this. Oh God. Hold on. Okay, so here's the SIM card is exposed through the back of the casing, but yeah, it takes a SIM card.
Yeah, very cool. I think it's awesome. So I think after today, you may get some new orders. So now that we talked about your way you come up with ideas. There's a question on the chat that says, "What is the process like from idea to result? Can you give an example?" And maybe we may have already answered this, but can you give an example describing your experience with an interesting project and how the collaborative workdays look like?
And how the collaborative workspace looks like?
Mm-hmm.
Well, at VNL, I mean, obviously it's all collaboration and dealing, and interacting with other people. Usually, for myself, I just kind of daydream a lot, and I might have an interesting idea, and maybe it's an idea that turns into something that could be a viable research project. And then I don't know how to answer that question. I mean, it's more interesting for my own fun stuff on the side, because then I don't have to, I could do design reviews or anything. You can kind of just have an idea and have fun making it on your own. And for me, it's like candy. It's like, I can sit on the couch in the evening and work out a mechanical design for something, or an electrical design, or do some programming, and then start actually putting it together and iterating. And I have 3 3D printers in my own house, one of which is running right now. And I should show that too. And I mean, I'm not answering the question at all.
I think Barbara, you did. It's not a straight line. It takes a lot of.
No, every project's different.
Some project's different, and everything. How your thoughts come to mind. It's just a different organic way that comes up.
Yeah, and some projects are well suited to doing the whole thing, doing a lot of design work, and before you ever actually make a physical thing. And some other projects, it's helpful to kind of invert that strategy, which is what Elon Musk does with the Starship development program, where you just want to just kind of make something because you're not really sure how it's going to work out. Just make something, anything, and see how it works, and then go from there. All right, I'm going to share again.
So, for example, if you look at your phone project, how long did it take you to design that particular?
I mean, it was originally my own. It was, like I said, it was just a personal thing, and I spent a few months playing, in the background, just as a side project, building it, and then I put it away for a year because I got bored, and then I picked it up again and spent a few more months, and then I had something that actually worked. People liked it, and I liked it, and now once it turned into a product, that was in 2020. That was like right when the pandemic was starting, and I'm only now about to start shipping production units, and that's. Chip shortage notwithstanding, I'm having order delays on some of the chip components I need until the end of this year, which is very frustrating.
Go ahead.
I was just going to show the other thing that I said. I really like this thing, the blimp drive. Yes. This is a paramotor, and I had this idea in the car one day because I've been trying to think of ways of having a motor on my paraglider that didn't require a whole custom harness that has a motor built into it. I just wanted to strap it to a pre-existing gliding harness, and I had the idea in my car. I was like, oh, it's just I just need like a pole and put fans on the ends. I'm being overly simplistic with the lingo, but I couldn't. So I ordered just stuff like that evening, and I had it working within the month, and oh, it's great. It's great fun. So sometimes it's helpful to like not do any design on the computer, CAD work or anything, and just go straight to trying to put something together, especially in that case, because I had no idea how I was going to go about certain things. It only really comes together once you start having things in front of you.
Mm-hmm. I love the picture of you in the air. I'm not sure if I will be brave enough to do that. If they had to take many Dramamine just to get myself and my fears up in that sky. So I love that because that's awesome. Justine, I want to make us a quick shift to career path. We have a good number of students joining us today, and so did you always knew that you wanted? So did you always knew that you wanted to pursue a STEM career? How did you end up at being what was that path for you like?
So for me, this was a very strange path and not what I would recommend anyone else follow. I as a kid, I always loved science and engineering, but I wanted to be an airline pilot more than anything, actually. So I was going to school to do that, and I got my pilot's license. And while I was away at school, I started double majoring in physics. And then after the first year, I got homesick and stayed home and had like an identity crisis. And then I switched to physics completely. And then I dropped out of physics because it was hard. And then and I was playing in a string quartet at this observatory you mentioned, and eventually started working on a telescope there, and got in. And then while I was there, I started interning at Brookhaven Lab, even though I hadn't finished my degree yet. And I also met my husband at that observatory. That's a good thing. And okay, so I basically started working at BNL, and I was kind of falling into an engineering role without having a degree. So I had to finish a degree, and I finished a math degree because it was the fastest one to do. And now I've kind of moved into more even of a research role, publishing somewhat regularly. And I don't know, it's been a wild ride.
So do you always, so in that process you became part of the instrumentation department, right? And you have been ever since.
I've stayed ever since. Well, because it's such a great place. Why would I not want to be there?
Exactly.
And it is. Yeah.
It is. There's a question in the chat I think is very cool to ask. Now, do you have can you talk about what was the first engineering design or project that you did? If was that the LSST project, or did you had another one before that?
Oh, at BNL, meaning at BNL,
or in general probably, but at BNL.
Well, yeah, mainly at BNL, I guess you would say. I mean, like I said, I was working on doing stuff at the observatory, this public observatory that everyone who lives locally should come and visit on the weekends. But yeah, I came to BNL and went right into LSST, Vera, Rubin as my only and main project for almost, and I kept doing it for almost a decade. And the very first thing I did was to design, I think, a bracket or something like that. It's just a mechanical design thing. And it just kind of kept compounding as time went on.
Very, very cool. So I know that there, if a students want to pursue a similar career path that you have followed, what kind of courses do you think a student, and that is in high school and college, should perhaps consider? And perhaps internships are part of that equation too. Should they consider what kind of coursework would you think will help them prepare for that path?
Yeah, I mean, well, I didn't know when I was working on when I was going to school for physics that I was going to wind up in instrumentation. It wasn't until I was in instrumentation that I realized I love instrumentation, because I like hardware. I like actually building things. So you mean if students want to go into that?
Yeah, into the path that you're doing, into the instrumentation department.
The thing is,
or something that you do.
Yeah, maybe more than half of our staff are experts in electrical engineering, RF design, analog electronics. So any kind of, I mean, if you have a degree in electrical engineering, you're probably a pretty good candidate for our department, but also applied, physics with electrical engineering background, even more so. So if you're a physics major, maybe you want to take some electrical engineering courses, or vice versa. If you're an electrical engineering or another kind of engineering major, maybe consider taking a physics minor. But also don't forget to, I like, you want to do what you're passionate about. And if you're passionate about it and you really like doing it, you don't have to wait until somebody's paying you to do it. You can kind of just, do it as a hobby, and that's kind of, I think, one of probably the main reason I fell into BNL, to working in the instrumentation division so easily, and have somewhat, and have thrived there, because before I even got there, I was building, trying to build, exotic telescopes just for fun, just on my own time and money. And, and when you go to get hired somewhere, and they find out that you've already done certain things, that's very appealing. If I were to hire someone applying for a job in our department, and I see, oh, look, they're on this robotics team, or they do amateur astronomy, and they even built their own whatever, or you're a programmer, and you wrote such and such program just for the heck of it. If you love doing it, you'll probably fall into making money doing it. That I guess.
Yeah, there's a question in the chat that asks, how did you stay motivated and inspired during your research?
Well, the research itself is the inspiring thing. I mean, sometimes there's the burnout syndrome, where you get fed up with there's especially earlier in one's career, you might not be working on the projects you really want to be working on, or you were working on somebody else's project, and you have to follow certain constraints that you might not want to follow. But I mean, you have to just remind yourself that, if you're in a position to be able to do that, you're luckier than almost, most people. If you get a job for NASA, it's like, well, how many people get to work on things that go to space, or how many people get to work on world-class scientific instruments. It's that alone should be motivation. But hopefully, when you get even further in your career, you can be very directly inspired by the things that you're actually working on, just because it's it just makes you say, wow, for your own good. I mean, like if BNL said to me, well, we can't afford to pay you anymore, I'd probably still do all this. Don't tell them.
Don't say that too loud. That's very good. There's a question on the chat that says, were you always taking things apart as a kid?
Yeah.
All the time. Yeah. There is, I think one question that, I think there are two questions that are kind of related. And I just asked both of them. What is one project that you have worked on that excited you the most? And I think that's kind of tag along with, there is a question about, predictions, the big stuff in your field as your field growth.
Yeah, well, so when I was on Vera, Rubin, LSST, it was that. When I was on BMX, it was that. And now that I'm on the working on quantum communications, it's definitely that. So right now it's the current project, it's quantum communications, mainly because I'm excited about how it can enable, basically, if you know anything about, again, if you've seen the movie Contact, you know that radio telescopes often come in arrays of, they come in big arrays, and you can make very high resolution images that way. It's not impossible to do that with optical telescopes, but it's very hard. It's practically impossible. So the technique that we're trying to develop now would, it looks like, conceivably enable the possibility of networking optical telescopes into an array the way you can with radio telescopes, and making mind-boggling high-resolution images, like imaging continents on distant exoplanets kind of thing, which you could only do if you push to the quantum limits of physics, not just the classical physics limits. So that's extremely exciting to me. Yeah.
And that's also where you feel the field is moving towards.
Yeah, I mean, you see, Yeah, I mean, especially with ground-based astronomy now, everyone's complaining about the Starlink satellites, and the low Earth orbit is only getting increasingly congested. And I don't even necessarily think that's a bad thing. Space-based will become a thing. Clusters of smaller telescopes will be a thing. I suspect that the large 30-meter telescopes that are being built both by Europe and the U.S. now are, I don't think they're going to get bigger than that. I think the future telescopes will be arrays of smaller telescopes, or they'll be space-based or on the moon.
Yeah. So that brings me to a question that I received by email about which instrument on the James Webb Telescope you are most excited or curious about.
Okay. Well, I guess clear to me, pretty pictures you can't beat. So there's an instrument called NIRCam, the near infrared camera. It's the main imaging camera for 0.5 micron to, I think, 5 micron wavelength. So that's, sorry, 0.6 micron to 5 micron. So that's actually red, visible red, overlapping all the way into the near infrared. And those, you know, when you think about the Hubble Space Telescope and all the incredible awe-inspiring pictures of that, it's mostly more or less visible. And so visible imagery is spectacular and awe-inspiring. And James Webb won't be as sensitive toward the blue as Hubble is, but almost. And actually the infrared, near infrared images penetrate through clouds, space clouds, you know, dust and stuff readily. So you get this incredible transparent effect to near infrared images. So that's just for the sake of the wow factor. That's the one most exciting to me. Yeah.
Very cool. There's a question in the chat that asks, have you ever failed or uncompleted any projects? How do you deal with them or bounce back?
Yeah, well, I have more failed projects than not. I have a whole graveyard of unfinished projects in the basement. In fact, the phone that you mentioned very nearly was one of those. I mentioned I put it aside for at least a year. I mean, yeah, that's tough because for a long time I thought I was in this rut where I would never finish a project, and you still get to be in that mode sometimes. And then for every 5 I start, if I finish one, I have to figure, well, you know, that's okay. I mean, I'm not going to finish every project. The important thing is that you're having fun. We're here for a short time. Let's have fun while we're here. Of course, you won't be able to be, you know, making a living at it if you don't actually finish the project. So some success rate is important. But yeah, I certainly have a lot of unfinished projects. Yeah.
Yeah. There's another question that we get in the chat, and I would ask as in the poster that we used in the flyer that we used, we put a picture of you that you're holding a Raspberry Pi. So what kind of, the question is, what were you doing? What kind of work that involved that, if you remember?
Which picture? The picture that was on when you first started?
In the flyer, yes.
In the flyer. No, that wasn't a Raspberry Pi. That was one of the, that's
that's the one of the
front end electronics for the Vera Rubin sensors. It's the readout electronics for the sensors, which actually I really don't like that picture because when I was working on a project, at the time I was mostly working on mechanical parts of it, some optics, but a lot of the cryostat test hardware and things like that. And the photographer came one day to take some pictures, and he's like, "Oh, hold this in front of you. That'll look good." I'm like, "Okay," and that turned out to be the picture, which I wasn't as really directly involved with it at all. So now I do work more with electronics and do electrical design. But at the time, I felt really awful. I still feel awful about.
It's a great picture, Justine. I will say, I really love it. So one thing that you mentioned, and because we're getting close to our end, but I want to touch about this. You mentioned mentors, and we talked about mentors and how important they are. Can you share a little bit how important having these mentors have been for you, you know, throughout your career?
Yeah, to me, I mean, so my current supervisor is still, I'd say, the person who's been my primary mentor absolutely since I've started at BNL, which is 12 years now, something like that. And I mean, I'm a different person than I was when I started. I am not the same person. Even 5 years ago, everyone can say that. But in terms of having the skill set that I have now, I see my time at BNL and under the tutelage of my the person I consider to be my mentor, Paul O'Connor. to be really the more important component of my education, more so than university. Absolutely. Yeah. I mean, I don't know what, I mean, you're lucky when you find the right mentor and you are able to get into a program where you're able to have a mentor. Yeah.
Mentors are important and they are very impactful in where we go and the impact that they do into our lives. Justine, we're almost to our end.
Okay.
If nobody remembers anything that you said, can you share one thing that you want to take away for our audience today? A take-home message.
Yeah, the one takeaway, I did mention it briefly, but I mean, if there's something you're passionate about, something you love doing, whether it's technical or whatever, don't wait for someone to pay you to start doing it. Just if you love biology, get a chemistry set and start doing it. If you love mechanical engineering, get yourself a 3D printer or a little milling machine and start doing it. If you love electronic, I mean, even if you're working at McDonald's and you don't have a lot of money, it doesn't matter. Buy yourself whatever tools and hardware you need to do what you love doing, because it will it just seems to work out. If you're doing it already before you get the job that you want to have, you're already you're already in that, you're gonna get it.
It's a very valuable advice. Just follow your passion, your heart, and do it. Take the risk and do it.
Yeah, take the risk and do it. Yeah, I mean, don't wait for someone to tell you you are endowed with the you are allowed to do it. Just do it.
Just do it. Awesome. Thank you everybody for today's Justine. My pleasure. It was a pleasure having you here today. I truly mean it. We will post a recording about a week after the today's event, so keep an eye for that. Thank you, everybody. Thank you again, Justine, for sharing your work, your wisdom, your advice, your inventions, everything. I'm truly appreciative of having you here today. Our next Science Thursday is February 17th. Our guest will be Carlos Soto from the Computational Science Initiative. We would like to thank Brookhaven's National Laboratory for hosting today's event, and I encourage you to check our programs and research internships opportunities at the Office of Educational Programs at Brookhaven Lab. Thank you, everybody. Stay safe, be well, and see you next time.